Yes. Okay. Everything set?
Yes.
Everything's set.
Okay, so as I said before we go into some examples and dive into the code a little bit, let's give to those who are not familiar with the trail or the Testarossa intermediate language, how it looks like, because it's a little bit different than other intermediate languages. It's a little bit different from LLVM IR. It's a little bit different from the bytecodes as they are used in not only Smalltalk but also Java VM and Ruby VM and everything. So the intermediate language is something that the front end, the parser should produce, and then the backend generates the code. And essentially, the trail is a tree-like structure. In fact, it's not a tree; it's a direct acyclic graph because you can share nodes. But I'm not doing this now. But you can think of it as a tree, and the node sharing is just to optimize things a little bit. So it's a tree of nodes, and each node represents an operation, and the operation is defined by opcode. So all nodes are the same. I mean, those are the same kind of objects, but they have different opcode, and the opcode defines what it does. Like I add adds to number. There is a call that calls a function. That kind of thing. The operands of the operation are the node's children, and there is a ordering which is defined by pretty much only by the parent and child relationship. So in order to evaluate parent, you have to evaluate all its children. But other than that, there is no ordering. But that's probably not that important. The key thing here is that the nodes or opcodes are typed. So the opcode produces some kind of abstract value only of a certain types, right? So you have a 32-bit integer, 64-bit integer, 16-bit integer, 8-bit integer, float, like a single precision float and double precision float.
Are integers signed and unsigned?
No. They are in trail. They are let's say signed, but you have an unsigned operation. So when you want to do a signed addition,
it's like Intel.
Sorry?
It's like Intel. You have integers, and then
I would explain it like this. They are unstructured bunches of bits. Okay. And
yes,
code is free to interpret that unstructured mess any way it wants.
Yeah.
Yes.
A question.
Okay.
You said that the tree or sort of tree is a direct graph. Does it mean that the operands, the children, have no reference to the parent node?
Well, technically on the implementation level, they do. But it's only to be able to perform certain operations. I will talk about it a little bit later. Right?
So in your implementation, the operands know the parent, but not in the original Testarossa language, okay? Is that what you mean?
To be honest, I'm not sure about how exactly this works there. But I only keep the reference in order to implement a certain API.
Okay.
And
So it's so the fact that I keep the reference inside the implementation of the node is implementation side effect. It's not something that is in the definition of the IL. You don't need it.
you can think. I think you can think like this. You have imagine a tree. It's a graph, but imagine a tree, and at some point you perform some optimization, and you want to change the node.
Pocho, you're probably not using headphones or something because your voice comes with echo.
I am, but
It's hard to understand.
what about now? It's the same?
Now
Good.
it's fine, thank you.
With me.
Okay.
I think if Jan switches off his microphone, that
I think it's that, not me.
Yeah, but how do I switch off my microphone if I don't have this Zoom thing? Let me try to.
You have the mute button in the bottom left corner.
Yeah, but then I will have to have this window here,
Okay.
which is something I wanted to avoid.
Okay. Well, I will try not to talk too much. So
No, that's. I don't want that. I want a discussion.
okay. Well, if you hear me.
Okay, let me try this. Something like this. Okay, go ahead, Pocho. Or.
So I was saying, Leandro, you can imagine the tree, but at some point you are doing some arithmetic operation or something like that in that part of the tree, and you can optimize it, and you can remove that node and put the results, right? Can you imagine that?
Mm-hmm. Yeah.
Okay, so it's like the nodes, the tree is like an AST, you can imagine. So when you remove the operation and you replace with other, you have to go to the parent and tell it that the new operand is a different one. So that's one of the reasons why you want to have a pointer from the child to the parent, so that you can go forwards and back from the parent to the child and from the child to the parent.
Okay.
That's it.
Well, that's assuming that children have a life of their own, right? But if you are performing the graph transformation top-down, then the parent actively knows that because he is the one who initiated the evaluation of the child.
Yeah,
right?
you can
Well,
implement.
maybe.
So let's say me is me, so Boris, and I have like, A and B, and I want to evaluate A. So I evaluate A, and now I replace my own A slot with the result of evaluation of A. So it's me as the parent of A who initiated that rewriting, and I update myself with the result. And frankly, I cannot really see a practical use of a situation when A evaluates itself out, sui sponte, and then says, "Oh, look, Boris, I am now, you should replace me with 42 because I just evaluated myself to 42. You should update and not point to me anymore." Right? It's always the parent who evaluates the child.
Anyway, guys, I think
it's an implementation detail.
I would defer this discussion a bit later because I think we are going into details which might actually
Okay, we are on a tangent.
make it
Okay, sorry.
more confusing. More confusing. I only started to talk about the parents and the children because mm, because the ordering in which you evaluate the values if you like want to compute the thing is not total, if that's the right mathematical term. I mean, if you have two children, all you are sure of is that the children are being computed before their parent, but whether the first child get computed first or the second, that's not defined. It can be both ways.
Right, there is no order of arguments.
There is no order of arguments. This is by purpose because then you can do the node value sharing, which is the way how you do a common subexertion elimination on these structures. But I'm not doing anything of this, and this is like a this is quite deep. I'm not there. It has its own problems, and I didn't squeeze this into literally 5 or 6 afternoons of hacking. But it's important to realize that the nodes are typed. That the top level nodes, they are called tree tops, but not all nodes can be tree tops. So there are constraints on the tree that only some trees are valid. It's not like any kind of combination of nodes and opcodes. So, for example, if you have a I add, which is a 32-bit integer addition operation, then its children could only be children that yields 32-bit integer, right? And if you want to add a 16-bit integer to 32-bit integer, you first have to do a conversion, and you have opcodes that do this conversion. But you cannot just plug the 16-bit integer under the I add because it will be invalid. So there are this kind of constraints, and one of the key points here is that at any single time we only allowed a valid trees. That simplifies a lot when you are working with those trees, and we will see how that can be done and how useful it is a little later. So as you can imagine, here's just an example. So if you have in some abstract language something like a plus b plus b minus 1, then you get this kind of tree, right? So we have an IAD, which does the I load, and then the other.
Are you showing something else? Because we say this tree and we are not seeing a tree.
Well, here.
No, we are not. We are just seeing the text, maybe, which says an example, but I'm not seeing anything.
Yeah, that's a for example, and there is a it's represented as, and below there is ASCII art of it.
But I am not seeing anything else.
No, I'm not seeing any ASCII art. Is represented as is the bottommost line that I see. Maybe your screen is not updating.
Oh, maybe your screen is not updating. Maybe just try to unshare and share again.
Better?
There it is.
Yeah, now much better.
Okay, sorry, I didn't realize that it's not sharing. So now you see the tree I'm talking about.
Yeah.
All right, so this is pretty obvious, right? For example, you cannot put, let's say, a const here, because the a const yields address, which is a different type than the isub expects. So, you know, a const here would yield invalid tree, and you are not allowed to do that. And when you are trying to build that code, or such a tree, it should fail quite soon and tell you can't do this. So you have this these trees, and on top of that you have a superstructure of basic blocks. But that's that's not really that interesting. That's for managing a control flow and things like this. We all know that. So here I try to outline a bit of I call it design principles, which is a bit of an overstatement. But these are the ideas I had in back of my mind for quite some time, and finally sat down and try to hack it to see how it goes. So the thing is that the opcode definitions are actually generated from the definitions from OMR. So they are one-to-one. They have the same properties. So if in OMR there is an isub, then here you have an isub that has the same properties. In the source, in the repository, you actually see some scripts that actually generate these definitions, which are then loaded into the Smalltalk from that C++ code. But it's just because I'm lazy to manually transliterate I don't know 500 of those opcodes. There are some really weird ones which we probably won't need ever.
500 opcodes?
Yes, 500 opcodes. 530, something like this. That's I was quite impressed, but keep in mind that, for example, for add, you have 7 variants because you have 7 types. Then you have signed, unsigned, and it explodes quite quickly. Then you for compare opcodes, you have compare equal, compare less than, compare greater than. So that's a 3 by 7 different types.
So this
for
is
floating point.
Sorry. This is different to LLVM, right? I don't know,
Sorry?
but I think LLVM has much less amount of opcodes, right? Am I correct or not?
Yes, I think so.
Okay.
I think so. But LLVM approaches certain things differently. I mean, I'm not saying I'm happy with those 500 ones, because there are things like monitor enter, right? That's absolutely insane opcode. But
Oops.
Sorry?
No, I have a sign here that says that my meeting will end in 10 minutes. I don't know why, because I'm using the pro version, and for some reason it's not recognizing it. So I don't know what's wrong. So I will restart the meeting if when it goes when it drops. I'm sorry about that.
Okay. Okay. So yes, but it's not like that. I won't have all these 500 opcodes implemented, and you need them. Actually, you don't need most of them, and it's fine. custom opcodes are allowed. So the structure allows you to from externally plug in the new opcodes, because opcode is just an object, right? That has some properties that drive the validation machinery. So you can clearly create the new opcodes, but if you do, then you must provide a phase that lowers those opcodes before you pass them down to the code generator. I will talk about this lowering later, but it's like in GCC or Clang, when you use a memset, then the Clang compiles it to a memset intrinsic, which is a LLVM way how to plug in new functionality like monitor enter without introducing a new opcode, right? So it looks like there are less opcodes, but the intrinsics here, intrinsics and LLVM, and these crazy opcodes they are pretty much the same thing. And then these opcodes are lowered into the instructions instead of proper function calls. Doesn't matter. So you would have to transform these custom opcodes into the base set, which doesn't necessarily need to be all these 500 ones, but it is so because I just generate them, so it doesn't bother me. I also decided that I don't want any fixed register usage, which means I need a register allocator, which means my life is much harder. But I think generally we are better off if we start with a proper compiler with a register allocator, even though it's really stupid, rather than starting with a simple approach with a fixed stack-based compilation and then trying to plug in the register allocator later and get rid of this. I also want to keep track of transformation. That's a one thing that is really hard to do in Testarossa. So obviously you have this IL, you build something, and then you run a bunch of optimization passes that destructure the tree, and it's really hard to figure out what has been rewritten to what and who did it. So I decided that I need a good support for this. So if I rewrite a code, then I rewrite a part of a tree, then the new tree would know from which it has been rewritten to, or what was the previous version. That should make a debugging of these transformations much easier. And also you can keep the context that did it the same way Boris did it 2 years ago when working on Coq. So you can see who did it and why and things like this.
And Jan, you apply several transformations to the original tree. You change them, so you go back one step at the time, or you just have a reference to the original tree?
This is not yet implemented, but I'm kind of thinking about having a copy on write on the tree,
mm-hmm.
And then keep every copy.
Mm-hmm.
I mean, I can decide to ditch the copy as soon as I'm the old version, as soon as I'm done with the copying. In, let's say, production mode, if I want to reduce the memory footprint or things like this, but I'm not there, and I'm not really sure I will get there.
Okay.
Well, maybe you want to verify the idea of a transformation.
Sorry?
So maybe you want to verify the idea of a transformation. So each time you do a transformation, you create an object that specifies how you translated something
Yeah,
to the
something
other.
like this. It's like my problem when I was working with Testarossa in the context of J9 back in the days was that my tree got rewritten and I had no tools to actually easily see who did it and why. And I want this to have a support for tools like this. The other thing, which I'm not doing now, but I think it's important, is not to lose any kind of debugging information. And even at the cost of generating slower code. But again, how much different that would be, I don't know, because probably we cannot afford to do overly crazy and advanced optimization. But if you ever
could you describe better debugging information? What's that?
Well, debugging information is a mapping from generally from the code you are executing to the source. Plus, locations of, for example, stack locations of parameters and other locals to their source names.
Okay.
And things like this.
Okay.
I don't know if you ever debug C++ code generated by GCC with -02, you would see quite a heavy loss of this debug information, so heavy that sometimes you just can't think. You are single stepping and it jumps randomly to completely nonsensical places in the source. You cannot inspect and see variable values because all the GDB tells you is optimized out, because the information where the value is just got lost over these transformations. So I just don't want this, because then you cannot debug anything. I also would like to avoid the common problem of saying, okay, for simplicity, I would only support one target, meaning, the architecture, and then, much later realize that that some of the decisions I did doesn't work really that well, and it also means I want to be able to cross-compile to multiple different targets, which is something that currently Testarossa cannot do. Unfortunately, nobody's happy about it, but there is, as I know the code base, there is little hope that would be solved anytime soon.
Sorry, what's the problem?
Well, the problem is with the Testarossa, the full C++ thing, is that you cannot compile it on Intel and let it generate code for let's say ARM and Power. It cannot cross compile. Okay, so let's continue. So I have few examples here, and as I said in the README and before, so far it can somehow execute these examples, and that's pretty much it. But I think it's enough to demonstrate the whole thing. So if we just run the simple example, we get it here. So you start with creating a TR compilation, which is the entry objects, and this code, if you can see it, is well, Do you see it? Is the font big enough?
Yeah.
Yes.
Okay.
Builder, I return, blah, 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 right?
Yeah,
I'm just
exactly.
being paranoid about freezing the screen refresh.
Yeah, I am paranoid now. Yeah, this is another why I'm always nervous. Anyway, so this is a simple code, and you see the tree here, right? So you build iReturn with one child, which is the iAdd, which has two childs. That's the icons 31 and icons 11. So that's how you build a tree. You know, that's the Smalltalk API. I couldn't come up with something simpler, but we'll do for now. And if we continue, then we go all the steps and compile the code. And if we inspect the thing, we have a little tool that show us the IL, so the trail code and the generated code. This so far only generates code for RISC-V, just because I'm familiar with it. So it was easier, and I don't have to think about how to generate the code or deal with architecture. I don't know in this phase, but I would like to have more. Anyway, what you see here is the transformation happened, right? Because originally we from iReturn we built the iAdd, which did the iconst 31 and the iconst 11, and there is this optimization pass. We can look later how that's done. That creates the icon 32. So we first simplify on the IL level as much as we can, and then we pass it down to the code generator, which generates this code. And for example, if we click here, we see that for the icons 42, we generated this piece of code. This grayish background instructions. And for the iReturn, we did this. Obviously, this is not the best code it can actually generate. We can load the 42 into the A2 straight away, but that's the limitation of the register allocator so far. So this is pretty much what it does, and this is just a decompiled MachineArithmetic instructions, which we can convert because they are all concrete or fully grounded if you want, and we can convert them to bytes and load it into the real target and execute them there. I'm not doing this in this test, but I did that when I was showing the RISC-V stuff on PowerLang on the last hackathon. So it's just a copy paste of the code. That's not what I wanted to talk about. So let's step a little bit, step by step through the code to see what is happening. So we first have to build the IL. Without the IL, we don't do anything. There's this build finished, which essentially fix up the basic blocks. I'm not happy with that, but it was just easier to do it for now this way. And if we inspect the compilation again, we see that we have this icons 31 and icons 11. We go over. Here we have the optimizer, which works on the IL level. And if we refresh, we see that we have now the 31. We can go over and let's see how the compilation actually progresses, because the compilation also happens in phases. So we go into, we create a code generator, we initialize code buffer, we generate a prolog, we generate the code. And now all the code is generated. So if we refresh, we see that we have all the code in place, except that we haven't yet allocated registers. So we have this virtual registers here. And we go and allocate registers and refresh, and you see that it allocated what used to be VR1 into A2 and what used to be VR2 into A0. And that's how we have it. Now you fix the branch targets, but obviously there are no branches, so you don't see anything. So this is just to demonstrate that we first work with abstract registers, just like Testarossa does, just like LLVM does, and then allocate them after we selected the instructions. Again, this is all built on top of MachineArithmetic, so we get this for free. And that's
what do you get for free using MachineArithmetic?
Well, the thing is that I can build I can have instructions which are symbolic. So I still have the instruction that has some parts of it not yet specified, like the register fields, and fix them up later.
Okay. So, and the optimization is done by MachineArithmetic too?
Which optimization?
The one you did to change the addition to the code.
Oh, here. No, this is on IL level, and MachineArithmetic only works, or it's a MachineArithmetic and ArchC, to be correct. And ArchC uses the MachineArithmetic and bit vectors to do these kind of things. Okay, let's we have continue. Okay, let's see. Let's run it again.
So sorry, a question. So in this case, you reduce the number of nodes. The optimization reduces the number of nodes. And where is the debug information?
Well, here the debug information is.
Sorry, or maybe the question should have been the transformations you did. Is something that you already implemented and we can see it? See that?
Yes, this is what I'm going to show you now.
Okay, sorry.
So now we go into the optimize.
Mm-hmm.
I wanted you first to get, how you build the IL and what is the result, and now we go how it does it.
So you're optimizing using manually written methods or using C3 or something like that?
Now it's just a manual.
Okay.
So again, this is not to show, or I implemented this optimization not to actually make the code faster. It's more to develop and test the API on tree transformations.
Yeah. Okay.
So we go into now. We have this trill simplifier, and now we place breakpoint because it would take ages to step through. But Well, yes. So a trill simplifier is a kind of a trill walker. That's an object that takes the tree and walks it top down. So the simplifier just walks the tree, and whenever you evaluate a node, it evaluates all its children first, and then try to simplify the node and return the simplified node. So we go into simplify, and we go into simplify arithmetic, and here I put the breakpoint. So if we continue here, we can single step. Yes. And this is all handwritten. So if we go step over, there are some conditions. Or simply, what is the node? BB start. We don't need that. Icon 31. We don't. Okay, this is the IAdd that we want to simplify. And here I just test that we can reduce the constant, or do the constant folding if both childs are load constant. So we say, okay, node child1 opcode, because the nodes, the instances are all instances of trill node. They only differ what opcode they carry. So this kind of thing, you have to ask the opcode. And if you look at the opcode, how a slow const is done, you just test some bits. And this constants and properties, they all are auto-generated from the OMR opcode definition.
So wait.
Mm-hmm.
So can we inspect the opcode?
Yes. We can say, okay, opcode is a trill opcode named iconst.
Or maybe the node more than the opcode, right?
All right. The node is a trill node.
Okay.
Its opcode, well, let's say its opcode is IAdd. It doesn't have a symbol because some nodes have symbol. It doesn't have constant. Some nodes have constant, some don't. And it has two children.
Okay, and it doesn't have a type?
It doesn't have a type because the type is defined by the opcode. So.
But how many bits does it add?
Sorry?
How many bits it adds? Or the code has the amount of bits?
Well, if you look at it, so all nodes in a trill structure are instances of a trill node. There is nothing like a IAdd node and icons node and anything. They are just a one class.
Okay.
And what operation they perform, they hold on the opcode.
Okay.
And there are this 530 instances of an opcode, and the opcode has a properties.
Mm-hmm.
And it says, okay, the data type, the type of this opcode, or the type of the value this opcode produces is in 32.
Okay.
It has two children, and they are of a type in 32 and in 32. Doesn't need to be so, but IAdd is defined so. And it have a number of properties you can ask. So when you do transformation, you can ask for these properties
Wait.
Mm-hmm.
and make a decision on top of them.
Yeah. Wait. So the opcode has children and also the node.
Yeah, well, the opcode has well, it's called children, but it should probably be called children types, right?
Yeah.
But here I call it, or the instance variable is named children because this is how it is named in Trill, or in Testarossa. And
Yeah.
to make things easier for me, I try to name things the same way they did it, even though sometimes they haven't done a particularly good job of naming things.
Okay, I'm not criticizing at all. I'm just trying to understand. So
no, I'm explaining, right?
Okay.
Jan, a question. What kind of information do you get from the property add? Because I understand properties associative, commutative, but add, what gives you?
Or what that gives me? Well, that's just a, I don't know. It's a property of the operation. So, for example, all this I know that because it has a property add, that this operation does some sort of addition. So all the opcodes, for example, if we inspect a Trill opcode named lat, which is the 64-bit edition, you will also see that it has an add. So I know that it's some sort of addition. If I, for example, do iload, I see that it loads variable. So I also see that it has a symbol, and this is used partially to guide, for example, this simplifier, let's say, partially to guide the verifier or a validator, checking whether the tree is valid or not. So that's for what the properties are. And actually,
properties are not meant only for optimization, but for other things.
Yes, they kind of form the description of the opcode, what is allowed, what is not allowed.
So basically, this opcode or all opcodes have 3 flag slots, right? Which are prop 1, 2, and 3. Yeah. So it has to be a 64-bit architecture, or it uses only 32 bits for each property.
Well, it doesn't matter because if it's a 30
because
architecture, then it's a long. It's all Smalltalk. The thing is.
No, but I meant in the sorry. In the original version, you also have this prop 1, 2, and 3,
internal,
right?
That's internal to the compiler, not to the runtime. So
okay, but
this property, these flags, they never exist on the actual target.
No. I mean, in the compiler, what are defined as in the original OMR? You have also props 1, props 2, and props 3.
Yes.
And they are what, 64-bit flags, right? Or 32?
I don't know. I don't know offhand. I can.
They are some kind of C++ black magic. They aren't even like just regular integers.
They are actually enums. And you never know, how big the enum is. Depends on the compiler.
They are 32 bits normally, I think. It's an integer.
Yeah. Normally yes, but you can force it to make it less or bigger. And in OMR in Testarossa, they do absolutely insane thing to save one single bit.
Okay.
That sometimes drive me. I mean, it's great because they have very low memory footprint. But when you are reading the code, sometimes it's frustrating. But it doesn't matter. You know, I only took this definition from them and model them my way. It's just that I preserve information they have.
Fine. Okay.
So where we are here. So I know that I can do some simplification on this arithmetic node. I know that both children load the constant, and I just compute the reduced constant, I compute the reduced constant, create a builder with the same, that's just how to create a freestanding node, and then I replace the node which is being simplified with its simplified version. So that's how you do it. So I implemented all this simplification not because it gives me better code, but to actually demonstrate how you transform the tree.
So here, but you're replacing two nodes with one, right?
No. Well, yes, but essentially I have the IAD node, and I replace it with the simplified version.
Okay.
Right? And the fact that the simplified version have less children or more children might have, that's just my decision.
Okay.
Right? I just replace the node. The important thing is that when I replace it, the resulting tree must have been valid. So if I, for example, replace it with the not iConst, but lconst loading 32-bit, then this would have been invalid because the return expects returning 32-bit value. So there is this magic inside the replace with that checks whether it still results in a valid tree. And this is also for what the properties are used.
And for instance, if you have expression plus 3 in parentheses and then plus 4, you first maybe use the associative property to move the parents to the right, and then you perform this simplification with 3 plus 4. So you use 2 steps, I guess.
Yeah, all sorts of things can be done. I'm not doing them, and that's this is a well-known problem in the compilers, that you have these optimization phases, and you sometimes need to run the same phases twice at different places because some later optimization opens up opportunity to do the same optimization on some new code. But as I said, this is just to demonstrate that there is some API that allows you to transform the tree and have the basics of this mechanism in place.
Okay. No, I'm asking this because some years ago I implemented some logic for simplifying expressions in a mathematical language, and I had to keep simplifying each result until I got no change, because so my question was if you had that in mind also.
Yeah, that's certainly what we would have to do when we go into this optimization area, which we might or might not. Depends what will happen with this code. But yes, this is what happens.
Okay.
And what about loops?
Loops.
Yeah.
I don't have loops, but I have ifs, which I'm going to show now.
Okay.
But yeah, we can have a loops. But you know, with loops, then you have these basic blocks coming into the game, and I believe it's pretty much the same as the ifs. I mean, in terms of implementing them. Let me first show you then this example, which is more complicated, and it implements a signum function or the sign function, whatever you prefer. So let's, here the code is a bit more convoluted because it's more complex, but essentially you have the builder, and you tell the builder that there is a parameter to the function that is called x, and it's of type int32. Right, and then the signum is if x is less than 0, then return -1. I hope I got it correct. Else, here, if x is greater than 0, then we return 1. Else, we return 0. Does that make sense?
Yeah. Okay, the result is 1 if positive, 0 if 0, -1 if negative.
If negative. So we run it. We run it. Oh, remove breakpoint. Okay, and if we inspect the compilation again, we will see something like this. And this is a bit more complex because we have a lot of these basic blocks. So this is a linearized tree or forest, really. And it's BB start and BB end, and they just mark, when the basic block starts and ends. And if you have a jump, then this is the name of the basic block you jump. So if x is less than or greater than 0, then jump to basic block 2. Here. And then if it is otherwise return, right? So this is just from this kind of nested building, I create a linear sequence of basic blocks which have jumps in them. And here I have the code. So, for example, if I click here, I see that it jumps to this address, but also, you see that it selected this instruction, sorry, this trill node. So I know that, that this instruction was generated by this. And, one thing that I find quite interesting and unexpected is that, again, if I click here, it shows me which instruction it generated. So I was like, okay, which instruction was generated for the iload? And I thought, okay, there must be a bug, but it's not. Actually, it doesn't generate any instruction for this iload, nor does it generate any instruction for this iconst, because the iload, it knows it's a parameter, so it's already in register A0, and the iconst value, so the 0 value, I can find in register 0, right? And the surprising and unexpected result is in that I thought I would have to specially care about it, but the way how the registers are assigned, and the way how these instructions are generated gave me this for free. I mean, if you think about it, it's obvious that it does it, but I didn't expect it to get it pretty much without any effort.
So, but wait, so this iload, is it a load or is it a move?
Well, the iload is an abstract operation. So how you implement it on a machine,
but
it doesn't tell you.
It doesn't correspond to a load from memory.
Well, it might or might not, depending.
Okay.
Right. The thing is, the iload takes a symbol, and the symbol, we have. Compilation. Where do we have?
When you find this, let me say that in a few minutes we'll break again. We'll go through the same.
Okay. So it takes a symbol, and here I know that it's a parameter, so it's already in a register. So I don't have to do anything. I just pass the register value up.
Okay.
Right.
But so the instruction doesn't point to the, let's say, another argument instruction. It points to a symbolic name. Okay, so that's the thing.
We can show how the iload is implemented, or how the iconst is implemented. For example, this iconst generates a code, because I need.
But let me explain my comment, because I'm mind mapping what you're showing to the implementation that Big has for all of this, which is more similar to the LLVM in the way that each node is of a different type, so you don't have that each node is of the same time with points to the operation. That's one of the main differences, and the other is that for the arguments, it's like you have a argument node, right?
Mm-hmm.
So instead of referencing a symbolic value like x, you reference an operation. So you actually will have that the iload x will be a node that is actually the argument. Not, you won't have iload x. You will just have argument x. That's the idea.
Yeah. Well, oh shit! I can't inspect inspect the iLoad because of a bug in this tool. But if we do something like oh, we need to go here and children, and that's the iLoad. You see that it has a symbol, and it's a parameter symbol which is named x, and has a type int32. So that's how you know that it's a parameter.
Okay. Yeah.
So all parameters are passed as registers.
Well, not necessarily. That depends on the calling convention.
Okay.
But on RISC-V, yes, first 8 integer parameters are passed in registers, and the rest are passed on a stack.
That is the C convention. What about this? Does it use the C convention? Is it mandatory?
No, it's not mandatory. I mean, now I don't have a proper reification of the calling convention. That's obviously a bad thing. But in Testarossa, you have a different calling convention. So you have a JIT calling convention, which does things slightly differently than the system calling convention. Yes, if we are going to, or if I am going to continue on this, if there would be any value seen in it, then yes, the first thing is to reify the calling convention. So the calling convention would tell you where to find when to find the argument, how to build a prolog, and things like this. But the calling convention.
Hi there.
Hello.
Sorry, I got distracted for a minute and
So
I realized it was 5 minutes.
No problem. Okay, Leandro, go ahead.
no, yes. What I don't see very clearly. So you have this list of blocks. The blocks have labels or names that act as labels, so you can jump from one block to the other. So every block has a jump. I don't see how to read. I don't know how to read this. And when the jump proceeds.
But maybe, yeah, you can explain him the concept of a basic block.
Okay. So the question is, what is a basic block, or
how do you link them through jumps? That's my question.
right? This is something that is a bit blurry because I don't do it properly. But here, if you do a comparison, then that's where the basic block ends, and you have two kind of successor. One is the one you jump to, potentially using depending on some condition, and the other one is just the fall through. And while I'm building it, I just hold on implementation. In the implementation, I only hold on the entry block, and if you inspect it, it has a 3 tops, which are the contents of the blocks, and then it has first and second successor. It has some predecessors because you may jump to a basic block from multiple different blocks. For example, if you have an if and then you continue, then the point where you continue is another basic block, and you jump from both the then branch and the else branch. So that's why you have a multiple predecessors or none for the entry point. And then you have next, which is just a link. When you linearize them, this is just like a linked list in which you process them and generate. I'm not sure whether it answers your question.
Yes, but so each of these blocks already knows the predecessors. You don't have to find them each time you want to. Okay, sorry.
No, maybe I will show you the builder.
Because in the implementation of the optimization at the bytecode level I have in pure-Smalltalk, I don't keep track of predecessors. I have to chase them every time I need them.
There are some compilers which actually, when you are building the IR, they don't really keep track of basic blocks. And once you are done, it infers the basic blocks from the IR. In both in Testarossa and in Tinyrossa, the concept is that you always keep the control flow graph, or the structure of the basic blocks up to date. Mm-hmm. So that's just a different way of doing. If there is quite a lengthy document in OMR that describes how it works there and why it does it the way it does it. I am not following that exactly as of now because of the time constraints. But I intend to do the same thing, and I more or less keep the control flow graph always up to date. So, for example, if here when we generate the signum, we use this if then else method, right, in a builder. Mm-hmm. So this is how it works. I first assert that it's a compare. So again, that's just to fail early. If you are building the IR and you do something wrong, it should fail as soon as it can. So that's another, for example, if you do how is compares implemented, it also tests the properties. So that's another case for which they are used.
Yeah.
So if it's a if, then I first check things, and then I allocate the block. The then block, else block. I allocate the labels for those blocks. So, Pocho, I shown you, that the iLoad takes a symbol, mm-hmm. And the symbol, in the case we want to load the X, is a parameter symbol. So the label is another kind of symbol, which means that you can load the address of the jump into a register, and then you do indirect jumps through the register if you want to. For example, so this is why it's separated this way, rather than having load argument and load temporary and load something else. anyway, this is how OMR does it, and I find it good enough, let's say. So you create the merge label, and then we link the blocks, and we set the block for where we continue generating the IL into the merge block. The interesting thing is that if you add a return into a block, it unlinks the successor, because obviously then it doesn't jump. If you return, it doesn't jump into the successor. There is no way to jump on it. So this is how you automatically get rid of blocks that you don't need because they are not referenced anymore.
Sorry, I'm not following that much. Can we
yeah, maybe that's too much. Yeah.
Summarize what we are seeing here, what you're talking about a little bit, because I need to go up a little bit in the abstraction level and see what we are doing, and then come back here.
We are this is how the if method on a builder is implemented. So it creates a blocks and some labels, so we can jump.
Okay.
So the labels are in the symbol manager. Then it links the blocks, so we still have the basic block structure. The control flow graph is properly set.
Okay, so the successors are not in the operation, in the jump operation.
No, they are in the block.
Okay. But this is a difference, another difference from the way we does it, because in the end of the basic block, it will have a jump to the next operation. So when asking for the successors, you go to the last operation and ask it for the targets. So if you change the jump for something else, you know how to set the successors, but still you have for each block the predecessors, but you only maintain the predecessors.
Right.
So you were saying that if you return from the block, I don't remember, but so you have multiple return points, or you have a last node that returns?
No, there are multiple exit points. If we go here, you see that this iReturn is here, which just loads into the return register and jumps out. There is another return here, and it's here. So if there would be some cleanup, like epilogue, cleaning up a stack, you would have it compiled multiple times.
Then that's another difference between the Tinyrossa and B, that in B you just put one basic block, which is the exit block, and then you jump to the exit block.
You could do this here as well if you choose to. Yeah.
It simplifies other algorithms, I think. Maybe it's not that efficient because you have a jump before a return, but you can also make the last code generation step to avoid.
Well, on this particular topic, years ago I did an experiment on Intel, and whether you have multiple kind of epilogues at each return, or you jump to one shared epilogue, it made absolutely no measurable difference.
Okay.
But it's one of those things, like how you like it, what certain designs allows you and disallow, and it's often like for some things it's better to do it this way, for other things it's better to do it the other way, and sometimes you just have to flip a coin and say, okay, I like this more. for
No, but I
complete-
think that when you have to traverse the control flow graph, it's for some algorithms, it's useful to say, okay, this is a return point. So you can go backwards to a place where something is defined. So you have only one exit point. If you don't do that, you have to go to each exit point. You know, these algorithms that use the what is the name of this is the, sorry, I'm not, I don't remember the name. You have the domination frontiers and also
Yeah.
the post-domination frontier. So at some point you have to calculate all that stuff, and I think it's easier if you only have one return point and one entry point.
Yeah, I think it can be relatively easily changed. Obviously, I haven't done it, so it's like more wishful thinking than backed up statement. But yeah, I just did what Testarossa does in a couple evenings, and that's it.
Okay.
Jan, I would like to understand better something. So if you have this if then else, the next thing is in the merge block, right? And if in the blocks of the then and else, you have jumps to the merge block.
Yes.
If you have some return in the then or else block, then this you don't need the jump to the merge, because you
Yes. I will let me show you how that is done. If I build, there is a private build arguments. Is it here? No, it's in block add. So adding and removing, right? So when as you are building, whenever you add a new node into the block, you end up in this method.
Mm-hmm.
Right? So first I check that it's valid.
Mm-hmm.
And this first check tells me this is not this opcode must be kind of an opcode allowed for the top level nodes. If it's not, forget it. You cannot do it.
Mm-hmm.
If it has returned, if this block has returned, you cannot add to it anymore.
Mm-hmm.
Now you add into the collection. I set the block of the node. That's just, keep up the references. And here I say, okay, if the opcode is returned and I have a successor one,
you remove both the predecessor and the successor. Yeah. Okay.
Yeah.
Okay.
Because I cannot get out of them.
Mm-hmm.
So in this signum, I return in both branches. Therefore, the merge block I created because I have to in the if, but then it gets unlinked from the control flow structure here. Therefore, I generate no code for it.
Yeah.
So you don't even see it in this list because it just gets gone by this. And again, here we use tail up code. This is how I test whether it's returned, because you have a return for each type. So yeah, that's how it is. Okay, any other questions before I go to the last topic?
So each return is a property of the opcode. Okay.
Yes.
So the opcodes also don't have subclasses for opcodes, right?
I don't have subclasses for opcodes.
Okay.
It's flat.
It's like a C version of
Exactly.
object-oriented programming.
Exactly.
Does
But I wanted this to be because I decided to take the IL from Testarossa for reasons we can talk about, but I'm not sure it's interesting. And because this is one of the main idea behind this, I want this part to be as similar as the C implementation or Testarossa implementation as possible. So I can check how the other guy's doing it, and that kind of thing.
Okay.
and isn't this creating too many is that code?
No, actually, you have less than in an object-oriented version because you have only one is return. If you have the polymorphic version, you have to implement it on the base level to return false.
No, yes.
Yeah, I mean,
but
that's the thing, whether to test thing and do something conditional or dispatch on the thing.
Now, what would be a little bit more confusing is that you lose the separation between different types of objects. So you will have to add return related methods to opcode and also branching related methods to opcode and also arithmetic methods to opcode. So they are mixed there. But yeah, it's a design decision to optimize something else.
Maybe it's a matter of taste, I would say. But yeah, but the main motivation is to keep this part really the same as much as possible.
For comparison.
Yeah, for comparison and yeah. And actually, let's say so far I wasn't too unhappy with this approach.
Okay.
Because for example, if you would hear dispatch on the opcode object, you might see it that it's better and maybe it's better, but for me the disadvantage is that I have the logic of what does it mean to add a node into a block in two different classes. Whether that's good or bad, I don't know. But so far I'm happy with this.
Yes, the other approach will take you to the sorry, to the visitor pattern.
Yeah.
Somehow. So okay.
Okay. Any other question?
Well, I have one question. The instructions, are they named? Are they not named? Because this is a problem I usually have, like when inspecting the intermediate code. Like these icons is the same than the other icons I'm seeing in this other place, or are they different? So do you have a naming policy or some way to recognize which instruction corresponds to which place?
Well, if you look, for example, and I click here, you will see that it selects me the IL node.
Yeah, but
right?
I'm talking more about the things in the left.
In the left.
Because when you start having greater basic blocks or a bigger amount of basic blocks, you stop recognizing what something corresponds to something else. Like, for example, when you start having an instruction that references another instruction that references another instruction, so you don't know where that instruction comes from. I don't know if I'm explaining myself.
I'm not sure what you mean. Obviously,
suppose you have a method that does an argument plus another argument, and then you inline it into another method. So in the bigger method, then you have more variables there, and you have to know which variable represents.
well, the nodes are, you know, identically different objects, so they are not identical.
Mhm.
Yes, you can number them, and you can display the number, you know, as a string. I don't, because I cannot inspect here because the tool is broken. But you know, if I inspect the model, for example, here, oh, this is unexpected side effect. But anyway, for example, you know, the inspector here numbers them, so you can distinguish that they are different, not identical objects. But yes, you can number them, and actually numbering the nodes and give them, you know, some unique number within the sequence is useful when you do the sharing. So in Testarossa, these iLoads will be the same node, right? Exactly the same node. They would be shared. And you will see that they are the same. I don't know really.
Maybe we can go forward and then continue with this so that we don't lose time.
Okay, if there is not any other question, I will show you something that is arguably super stupid. It doesn't work, but I kind of like it so much that I have to show you. And that's how I do the register allocation, which, sorry, doesn't work. It's stupid, it's bogus. But when I was about to write the code generator, generate the code, I was facing the problem of okay, now I really cannot avoid writing the register allocator. And then I was sitting for 5 minutes and thinking, what is the most stupid way, you know, the most simplest, stupidest way to actually allocate at least something that would work for those examples. And then I come up with this, which I wrote in literally 5 minutes. So what it does is essentially it uses Z3 as a constraint solver. So I take all the virtual registers, all the real registers which I am able to allocate. I extract you know, the dependencies, and then I say, okay, give me such a mapping of these, you know, virtual registers, these names to the numbers, such that there is no conflict, right? So this is just this. You know, here I go through the registers. And you know, one of the constraints is that if there is an instruction, then it must use different registers for different operands. If there are virtual registers, which in some cases I have to force to map to a real register, for example, for the return, you know, when I'm moving into the return register always must be A0. So that's the constraint. And here is a constraint that for each virtual register, it must be one or the other or yet another of the register which are actually available for allocation. And in the end, sorry, I just say, okay, solver, give me the model, and I extract the allocation and set the allocation out of the Z3 model, and here is just how I replace them in instructions. It's really stupid, but it was really easy to find, and it actually does allocate registers for these signal methods. There are not many, sure, but I kind of like it, even though it will have to be replaced with something better.
Wait, one thing I didn't see is if there aren't enough registers, it does moves. If there aren't enough registers.
Oh, obviously that's what the comment says. If it runs out of registers, it fails.
Okay. It could add moves, right?
No, it does. It cannot handle
pushes.
spills. It cannot handle spills. It cannot do pretty much anything, but enough for allocating registers for these examples. But again, I didn't want to spend a couple days writing a register allocator.
It's very nice. And you said you are in a constraint that all operands in the same instruction have to be in a different register.
Yeah.
I guess that's it's an overstatement, because
yeah, it is overstatement, but then I didn't have to deal with live ranges and things like this.
Okay.
You see, it's stupid, it's bogus, it doesn't work, except for these little examples. But yeah, if there is anyone who is willing to write a proper thing, I would more than welcome to.
So could you repeat the constraints? One is have different registers for.
Well, the first thing is that for all virtual registers which are allocated, and I just, whenever I need a new register for new value, I just allocate a new virtual register. There are unlimited number of them. Mm-hmm. One constraint is that, well, let me see, that every virtual register must be equal, I mean, the number of it, 1, 2, 3, and so on, must be equal to one of the registers which are available for allocation. Right? So that's the OR. So, the virtual register 1 is either equal to x1 or equal to x2 or equal to x3 or equal to x and so on for all registers.
So this is all virtual registers must be assigned to some
register.
Yeah.
Some physical register.
Okay.
So that's the first constraint.
Yeah.
That's obvious, right?
Yeah.
The second constraint is that the constraints put on the virtual registers must be satisfied. So, for example, when I'm allocating virtual register for the parameter, because initially I work only with virtual registers, then I know that the parameter is in A0 because that's what the ABI says. I cannot change that.
Okay.
So this is where these constraints comes from. Right? So if I'm allocating a virtual register for a parameter, I know that it has to be A0. Similarly, for return, I know that it has to be also A0 because it's also a return register, like EAX on Intel. If you have instructions which only work with some registers and not with others, you would use the same mechanism of the constraints. You just force them to be, whatever constraint is. So these constraints put on virtual registers must be also satisfied.
Okay.
And the third is, for each instruction.
Yes, that's clear. So you force all parameters of the instruction to use different
different registers.
Okay.
That's too strong. Sometimes that would need for more registers to be allocated than it's necessary. But it's simple to do with a simple structure without actually computing, where the registers are used and all that kind of things those register allocation papers are talking about.
Okay.
And then I just feed the Z3 solver to give me one solution for this.
So wait, but this rule about using different registers, how does it? So it doesn't guarantee that liveness is respected.
Sorry?
So, okay, so you are using a different register each time, right? I mean, there's something I don't get.
Well, the thing is, if I have, for example, add VR1, VR2, and VR3, like these virtual registers, then if I know, for example, that VR2 is not used after I execute this add, I can reuse the physical register I use for the VR2 also for VR1, right?
Yeah.
But I don't compute this information. I don't keep this information.
But the rule is
to be on the safe side, I force them to different.
Yeah, but what I'm saying is that the rule doesn't keep that property. It just says that the different registers have to be assigned to different real registers. Like you will have real register 1, real register 2, real register 3, right? If I'm correct. But
Yeah.
then you might say, okay, a second instruction that says add virtual register 4 with virtual register 2 and virtual register 3, and it would, okay, it wouldn't assign to virtual register 2 anything, I guess, because each operation has a new register, but then you are just giving a number to each register, right? Each operation generates a new real register, basically.
Yeah,
So
pretty much.
You could just have said, okay, so this operation has register 2 and register 3 as operands. Which are the registers? Give them to me, and now register 1 is the real register 1, and it's nothing else than that.
Yeah, perhaps.
It's like linear counting. Like this new register is register 1 for VR1, and the next one is...
Maybe I tried to be a little smarter, and but as I said, I write it in 5 minutes. Then it did the job I wanted, and I didn't thought about it for a single second, because as I said, my goal is not to write a register allocator. My goal was to put all this in place and see how what kind of shape it takes.
Yeah, I understand the idea is it's very interesting. I mean, when doing the full stuff, what I was saying is this is like thinking you have infinite number of registers and adding a new register to each operation, a real register. It's not really allocating registers in a way that.
No, it's not. It's not.
It's like saying, okay, virtual register 1 is register 0 or register 1, and virtual register 2 is register 2, and that's it.
Well, you have these constraints but whatever. Maybe I shouldn't have talked about it.
No, it's nice because the idea is nice. It's just that I think that's there we are.
So,
okay.
Jan, to summarize this allocation algorithm, my understanding is you didn't want to hard code the registers, the actual registers. So you needed some allocation algorithm, and you implemented the simplest one that cross.
Exactly. Exactly. I wanted to be a little smarter than just. Oh. What is this? Hello.
Yeah, that was some temporary
Okay.
problems, I guess.
Okay. So yeah, it was the simplest thing. I tried to be smarter than just assigning them one by one. But maybe I failed. But that was not the point of this exercise. I know that this was just to be able to generate any code that does something, not really working on that and spending more than absolute minimum I could.
Okay, but if in the future you plug any other allocation algorithm,
yeah, if this is to be used for anything beyond these 3 examples, yes, there would have to be a proper allocation.
Yeah, I have a further comment on this, but let's postpone this maybe for a few, for 10 minutes or something, because I think this relates to a bigger problem. But let's not, let's postpone this.
Well, I don't know. At this point, I'm showing
this about the allocation, and this thing what Pocho just pointed out is a larger problem.
Well, everything in this is a larger problem, right? We don't have a proper linkages. We don't have this, and we don't have that. But at this point, this is pretty much everything I did. There is some code we haven't seen, but that code is probably boring. So at this point, the question is it really useful for anything then as a tool for me to procrastinate on some other work? Or yeah, the question is actually what to do.
That's a question for me, I guess.
Well, that's question for
I have a very extended answer, but I will let others speak first if they also have their own, because mine is gonna be somewhat long.
I would like to understand the goal of this project. It is just something, is an exploration, and if in that case, where are you coming from? I mean, why are you doing this? Just for fun or what?
Leandro, I can take that. Pocho?
Yeah, the question I was going to comment was that in B we have also a kind of optimizing compiler that uses its own IR, more similar to the one of LLVM, as I said before. And it's interesting to me, or for me, to look at others and try to steal stuff. So, for example, there have been many things that I've been that I want to implement in that compiler, but I never had time, so I never did. For example, one of them was to add typing information in this compiler that we use. Is everything is an object of typed object. That's what I mean. So, for example, when you have integers, if you want to add them, you have to assume that they are small integers, and you have to cast them to native integers, add them, and then cast them back to native integers. That's the way you do any operation and things like that, because everything is stored as an object. And having type information would make the code much more efficient, because you could say, okay, this came as an object, but now we have it as a native integer, or maybe it's a constant, but the constants even are objects. So you can cast them, or not cast them, but you can use them as native integers if you have proper type information. So yeah, for me, that kinds of things, looking at other code and even having people explaining what they did is much better, because I can try to take that information to improve the B intermediate representation. So for me, it's interesting, yes. I would say that adding loops is not like adding branches. It's much harder than that, because you stop having trees and you start having cycles in your graph, and everything becomes a mess and very complex.
I can certainly try.
Well, I could also take both Pocho's questions, but okay, Jan, go ahead, and I will.
Well, let me first answer Leandro's question. Well, the goal. I don't know. It doesn't have a goal. At this point, it's an experiment. I was thinking about playing with this in this direction for I don't know, 2019. We discussed this with Boris. I don't know what was the San Jose, Santa Clara. I don't remember. Anyway, so I was thinking about playing with this and see how it goes, because one of the things I was also thinking, and I'm probably not going to show this today, but that's how you can progressively lower. You build this IL with a very high level nodes or opcodes like a cent, and then you progressively lower them to these base nodes, and that's how you can build a Smalltalk compiler, for example. The other motivation is to actually look into what the operations really do. Right? When I was working back in the days on the Testarossa RISC-V, I had to implement what for example I add and things, and these are relatively simple. I mean, everyone knows what they do, right? But there are some crazy opcodes. For example, overflow check, or floating point compare. Right? You would say floating point compare. Less than. It's what it does. But when I started asking questions, OMR developers, it turned out that every single one of them have a different point of view what it should do in a number of corner cases. Like, one of them is none, one of them is positive none, positive zero, negative zero, and it turned out that that their implementation on different architectures differs. So, and there is no formal way of or formal description what they do. It's like you read the name and it should be quote unquote obvious from the name, but it's not. And now we have this crazy machine arithmetic refinement times prover Boris did, and we can probably formalizing what they do, which would be quite an interesting application. But beyond initial experiment, I have no further goals. That's why I actually call this meeting, and why I'm asking for a feedback early on, so I don't waste time on this. If everyone says, well, nice, but there is nothing new, and we have other things, and then there is no point. That's so there is no really any long-term goal than just having some fun, and build something I was thinking about for a long time, and see whether it flies or not. And that's why we are here. Okay. Did I lose everyone?
No, we're here. We're here.
Okay, well, everybody else is silent. I'll tell you my feedback on this. This is better than any expectation I was ever dreamed of hoping. Let's compare with the original goals we had in mind when we were discussing this back in Santa Clara or San Jose, whatever it was, 2018, 2019. The modest goal that we were talking about was simply to bring in with the work, the whole community, the most advanced VMs, such as J9, the techniques that they use in terms of IR design, because we have the goal of this small talk of the future, and in small talk we have bytecodes, and that's all we have. That's all the IL that's available to us, and it's obviously not as simple as, oh, we'll just use some whatever blue book bytecodes, because obviously people are designing their own bytecodes, and if you look at COG, in order to enable further optimizations, they have like what, 3-4 different sets of bytecodes that are specifically modified because the previous one did not work. And simply to try and come up with our own ad hoc design for an intermediate representation, such that it fits, for example, multi-core. It's inverse vandalism. There's a whole science behind that. these people who design bytecodes, they have their own conferences, they have their own journal, they have, you know, all kinds of, it's a whole science. So the modest goal was simply to try and somehow connect with their community and reuse the work that, you know, that actual community is doing, so that you know, we are at least aware of a bytecode design that is proven. Like J9 has been, you know, over 2 decades, and it works, you know, on huge machines for huge hundreds of thousands of processors accessing the same memory in an SMP fashion from Java, you know, from the same image, locking without, you know, crawling to a halt. So that was that was the goal there. This after actually seeing what this is, this solves much bigger problems than that. My biggest problem so far is, okay, well, we have this abstract interpretation engine that I built, and yeah, it's all good and it's big, and now we're coming to a point where it actually does work, like, you know, fixing all the bugs in it and, you know, properly like software engineering it, and, you know, having CI and you know, an actual test suite for it, and all, you know, actually working, other than just, you know, handwritten notes and pieces of experiments here and there and just demonstrating ideas. And that's all very good, but on the other side is we have this problem of boats, right? The ocean is so big, and our community, you know, the resources that we have, they're so small that we are in these little boats. That my boat, you know, where I am with the machine arithmetic prover, and the boat where, okay, well, you have the actual DMR VM, they are so far that humanly bridging that huge chunk of ocean is simply, from a resource perspective, you know, humanly, what is humanly possible is there's no hope. This is very interesting, because what I am seeing here, bridging and actually using the machine arithmetic and ArchC and the cleaver and this, you know, what I've done for formal proof of this Tinyrossa, the correctness of transformations over these trees is actually trivial. I think it's gonna take something like, I don't know, an evening of hacking. And the idea why this is only an evening of hacking is something that I kept, you know, kind of reading, and it's all over the Testarossa documentation, is that an opcode has a type. And a type is, you know, 32-bit int, or signed 32-bit int, or an IEEE float as implemented. I don't know, whatever is in anything, right? But when Jan said that same word and showed this, I'm like, but type can mean type in the Curie-Howard sense. So it's a proposition or a theorem, right? And then these trees, they are simply proof trees, and they compose for if we take the implementation of types as they are implemented in machine arithmetic, they compose, well, simply because they are subsets of Z3 sorts. So when I say a refinement type, right? I mean, you know, Z3 int such that a Z3 int x such that x is greater than 10, right? And obviously, all of those Cousteau algorithms for static analysis, all of that works automatically, well, simply because they form a complete lattice under set inclusion, and then you have all these nice things. Now, an opcode is a type, right? It's a dependent type over the type of its children. So, or it's a sheaf if you want, right? So you have add, right? Or add-I. So it's not just, or add-I 32, right? So it's not just the type, if we say the type is 32-bit integer. Well, if we say that, no. The type of I add 32 is an integer x such that x equals in machine arithmetic a plus b, where a is the parameter of the type of the left subtree, right? The left subtree is not just int 32. It's the subset of Zahlen of all integer x such that x equals a. And on the right hand, similar subset, right? It's all integers y such that y equals b. Then the refinement type of the opcode is all integers such that all integers x such that x equals a plus b. And then automatically you get transitivity on these things because you get transitivity of partial ordering, and sets are partially ordered by inclusion. And then all of that stuff, how Patrick Cousteau and all of his school, how they implement an optimizing compiler over on top of that, it automatically applies to these trill expressions. Well, simply because they have the types are subsets. Sounds like being much theoretical, but I'm looking at the code and I'm looking at what the classes, what these classes look like, and it does look to me like actually connecting this with machine arithmetic is an evening of work.
Boris, so in your example of a plus b, you're using an operation that is in Z3, which is plus. So, but what if you have another kind of message between, say, A and B? You have support in machine arithmetics for a similar sort of checking.
You write your own, right? You write the specification of what the function does. right? And I will show you in exactly
and
what
you express that in C3 using the function, I don't remember the name, that tells you what you will get from the
well,
function.
you are not you are totally not limited by what is available in Z3 as like atomic functions, right? You compose your own, and the nice thing about Z3 is that it knows how to do combinations of theories. Like, for example, you can say one of the examples I use all the time is you have a list of objects of any type, right? So you have this interpreted function, these uninterpreted functions of some unknown type A. And okay, well, I have uninterpreted constants. A constant in Z3 is a point, right? Not an element. So it's a function taking the terminal object and returning, whatever. So you have those, and let's say a list is a list of elements of unknown type, and you have you have some functions that take, for example, a list of those things, and you try to prove length, right? And you try to prove that here is the definition of the length function that takes such a list, and so on. So you now have a combination of an uninterpreted, like pure, Babylonian equational reasoning, right? The only thing that you know about things is what is given by their syntactic, ASTs between them, right? So you have a free algebra. But then intermixed into that, you have non-free, like objects with non-free algebras. For example, integers, 2 + 3 is equal 5, not because of syntactic definition or, not the notation, how you write them, but some intrinsic other things, right? And Z3 can, when you ask Z3 to prove equalities that have functions that mix, these interpreted theories versus theory-free uninterpreted objects, that's Z3's, bread and butter. That's what they do best. So this is abstracted over any kind of structure, not just that you have integers or bit vectors, and Z3 gives you this already pre-made operation for you, right? You construct your own, and this specification of what a function does, this is what you take for the definition of what of what an opcode is. So there is a specification written as a dependent type or as a sheaf, because they are sheaves. And you attach that as the actual type of the opcode, and then you can plug them, because when you have a function that takes two opcodes, right, which is a node that is higher in the hierarchy inside the tree, they automatically compose, right? Well, simply because because sets under inclusion, they form a complete lattice, and all of that nice abstract stuff that leads to this Cousot algorithm, it automatically holds.
Okay. Okay. So your feeling is that this kind of implementation will allow you to express all of those verifications that you implemented on based on the C3, etc.
Yeah, I think not only it will allow, I think it is exceptionally easy.
Mm-hmm. Mm-hmm.
So that's that feedback. Now there were, I think, 3 other questions. One was
What is before that? In about 5 minutes, this will break again. I propose to stop there because we have been in the meeting for 3 hours, and we can continue whenever you want, if you like. But I think we can stop for today in 5 minutes. Is that okay?
sure. I mean, if people want to hear other things, then we can discuss. If people don't want to hear other things, then we can stop.
Fine with me. Obviously, if you have any questions or any comments, you know how to reach me.
My question is, Jan, did you have more things you wanted to show and you haven't yet, or?
No, that's everything it can do. I showed everything, not every single line of code, but everything I implemented.
Okay, excellent.
No, you, Jan, made me want to have a talk about the other one, the one in B, which I never explained to anybody. So at some point in the future, I will prepare a talk about it.
Sure.
But not very soon, because I have quite a lot of things to do. So yeah, I expect maybe, no, I don't know, maybe September, October, I don't know. But yeah, just wanted to say that. And just one simple question for Leandro. So the Smalltalk is confirmed, the place is confirmed, everything is confirmed?
Yes, yes, we will have the Smalltalk conference in November. Yeah.
Okay. Because at some point I had some doubts, like there were some things that were not confirmed, or it wasn't being publicized.
No, but it's now confirmed.
Okay.
We are sending invitations. Probably the invitations have already been sent.
Okay. I inscribed as well. Okay.
Okay then. Thanks for your time, and yeah, maybe see you some other day.
We still have 5 minutes, Boris, if you want to add anything.
Well, I don't know. People seem to be not exactly super interested in my answer to Pocho's 2 questions and the question about the register allocation. I don't know. Do you still want to
Or
hear
maybe people are tired, including me.
that?
We can leave that for another time because we have been concentrating this for 3 hours. But so it's a good time for a break. But for stop.
Okay, then let's stop now.
But we will have Boris. We have the other meeting for your talk and we can.
Oh, that's for my stuff. That's in exactly 1 week.
Yeah. So I will have to send. I have still to send the invite. I will first find out what's wrong with the account, the Zoom account. Once I have that sorted out, I will send the invite, and at that point we can decide if you can answer the other questions next week or another time.
Yeah, or maybe we could have, because obviously this is gonna this thing between this at some point, this 1 week evening of hacking between me and Jan is bound to happen, and it could be soon, right? So then maybe we could have another meeting on that.
Yeah.
And then we will much more visual answer to all these questions than just just hand waving and explaining and verbal argument and whatever.
I just wanted to add, especially for Jan, that this talk was very interesting to me, especially because I'm currently working on some similar things for this Smalltalk. So for me, this is very interesting. Also, because it gives ideas and allows me to think beyond my horizon.
Good.
Can you tell Leandro what we are working on B related to this?
Well, this is about to break, to stop, but I'm working on something similar, but but much closer to what you already have for the nativizer, etc. But yes, I will be happy to expand on that, but this is not the time. We don't have time yet.
Okay, so we have another 2 talks in making. That's good.
Yeah, maybe. Not sure whether my stuff is interesting, but at least I can tell what I'm trying. Okay, guys, let's stop here. It was very, very nice and interesting to attend this meeting. So we will meet again in a week.
Okay, thanks.
Okay.
Okay.
Bye.
Thank you. Bye-bye.